Today we're going to be doing exam 29 to 30, chapters 29 to 30, doing question 2. Question 2. This will be all about the electromotive force, how magnetic field acts upon it. So the first thing that's going to be talked about is going to be here, part A. It's going to be an isolated conducting rod of length 8 centimeters. Is oriented parallel to the x-axis. It moves in the positive y direction at 3.90 meters per second in the presence of a uniform magnetic field of magnitude of 0.6 Tesla. That point is in the negative z direction. Find the magnitude of the motional EMF in the rod. So, what we first got to do to be able to really understand what's going on is we have to really graph this out and understand how things are moving, because this can tell us a lot about the direction and then as well how the current is moving through this rod. So I'm going to draw a little 3D graph right here. So it's telling us that the rod is oriented parallel. So if our x-axis, y, and z were parallel right here, generally parallel, and we're moving on our y. So pretty much we're moving in the y direction at 3.90 meters per second. This is where our direction is going, so our force is in this way. But our uniform magnetic field is going in the negative z direction. So how we can write this is that force is this way here, going to our right, and then the field is going down, negative. So that means that our current must be facing towards us, because as the force moves in one direction and the field moves in the perpendicular direction, that means that pretty much the plane of those two directions, what is perpendicular to that, will then be the direction of the current. So these 2 points right here are creating, pretty much, you can visualize it as a plane. We pretty much have the YZ plane. Whatever plane is being created, the motive electromotive force, pretty much its direction, the electric field or the electrons, will then be perpendicular to that. We need to understand this. So we know that electromotive is equal to the velocity times the field times the length. So let's first figure out what our electromotive force is. So that's pretty much just going to be the values given to us is then equal to our velocity, which is 3.9 meters per second, multiplied by our field, which is 0.6 Teslas, multiplied by the length, which is in centimeters, which is 0.08 meters. So we'll just multiply that all together. So 0.6 times 3.9 times 0.8. That means that electromotive force could be 0.182 volts. Around that's 2.187, but that right there is our answer. So then it's asking us, what is the electric field produced in the rod for part B? Now, we know that the potential difference of A to B is equal to the electric field multiplied by length. But at the same time, electromotive force is also equal to our potential difference, since they're interchangeable in their own way. So that means that we can equal electric field times length is equal to electromotive force. So, and we know that electromotive force is equal to velocity field times length. So we could just say that the field times length is equal to velocity times magnetic field times length. Divide by length, take it out so that all we have is the field is equal to velocity times the field. So we're just going to input our values. So 3.9 times 0.6 Teslas meters per second. The field is going to be equal to 3.9 times 0.6, 2.34 volts per meter. 0.34 volts per meter is the electric field. Now, since we've already in part C, it's going to ask about the direction of the electric field. Since we already understood how these forces will all work together, we already know that our field is going to be moving in our positive x direction. Because what's pretty much happening is as the rod is moving and the field is going down, it's creating a force that's going to move the electrons within this rod all the way around. So it's going to move the electrons to this side, which would be the positive x direction. So that would be our answer for part C, the positive x direction. Let's move on to the next part. All right, so part D. This time we're given a figure. So, excuse for the noise. My dog might be playing with the toy. But, okay. So pretty much what's going to ask us here is, in the slideware generator, figure 1, just let me draw out figure 1 really quick. We're going to have our rectangular conductive loop. We'll then have a rod here. We got a velocity, electromotive force, and current, all within a field. So that's just to say that it is going, there's a field, magnetic field going through it. So, okay, so in this figure, if you reverse the rod's motion, so reversing it, meaning instead of moving it in the right way, moving towards the left, it moves to the left out of the right. The moving rod is 5 centimeters long and moves at 2.40 meters per second. And the uniform magnetic field has magnitude 0.150 Teslas. If the resistance of the current at a given instant is 0.02 ohms, find the current in the circuit. So we're just finding the current within the circuit right here. Now, this is very simple, because we're just be using the same formulas that we just saw the last time. Electromotive force is equal to velocity times field times length, because technically it is interchangeable in which movement we're taking in whatever area we're seeing as positive. So electromotive is equal to our velocity of still 2.4 meters per second multiplied by Tesla, which is 0.05, 0.150 Teslas, which is the field, multiplied by the length, which is 0.05 meters, because it's 5 centimeters long. Because we could just use how the current is equal to electromotive force divided by resistance. So we're going to first find electromotive force, which is 2.4 times 0.150 times 0.05. So electromotive force is then equal to 0.018 volts. So then we're just say current is then just equal to electromotive force divided by resistance, 0.018 volts divided divided by our 0.02 ohms. 2. So that's just going to equal to 0.9 amps for our current. Because the only thing that really determines a change within the current, or determines that there will be an electromotive force, is just if there is a change within the movement of the flux. So if this rod is moving in either direction, that will say that it is moving. Now, a really unique thing to see is that it's going to be, as long as it's moving, you're going to get some current going. Now, depending on direction will depend on either if it's increasing or decreasing, but either way, as long as our flux is changing, we know that we are going to get an induced current, which means that we'll always have a current moving as long as either it's moving in any which way. Now, since we know it's moving to the left, it's going to be clockwise, because as the field is moving this way, since it's moving through it, we can just say that the force is this way. As that plane is here, it's then going to be moving in the clockwise direction. It's going to be moving around. It's going to be perpendicular to it. And you can do the whole hand rule where it should be this way, and then it will then be the opposite direction. So it's hard to see because my hand is opposite, but if my hand was upright, you would see it. The force is moving to the right, the field is moving this way, and the middle finger will then point what is the direction of the current moving. Obviously, if we flip it around, because we're moving to the left, we then have it moving, the force is moving to the left, our field is moving through it. That means that our direction is downwards, so our electrons can be moving in a clockwise direction. And that's going to answer for part E, which it asks to find the direction of the current around the circuit. So it's moving clockwise. Now, obviously, if it was moving to the other side, it would be moving counterclockwise. So now we're going to move on to part F, where it's asking an isolated conducting rod at a length of 8 centimeters is oriented parallel to the x-axis. So at time equal to 0, the end of A is at x equals y, x equals z, and it's all equal to 0. And at the end of B, which is at 8 centimeters, it's then going to be x to be 8 centimeters, and then y and z are at 0. The rod moves with a constant velocity of v, and so it's going to be the vector v of 1.5 meters per second I plus 2 meters per second j, and a uniform magnetic field of a vector b, vector magnetic field b, equal to negative 0.120 Teslas I plus 0.5 Teslas k. Find the magnitude of the induced EMF in the rod. So, graph it out, visualize it. Let's see. Oh, whoops. So, we have a rod parallel to our axis here. Now, our point A is pretty much all at 0. You can visualize that this is at 0. And then our point B, to be up here, is at 8, 0, 0. Now the rod moves the constant velocity in a direction. So its velocity is moving from 1.5 to 2.0. And the magnetic field is also in its own vector, moving in a direction kind of negative, since it's I and K. It's moving in the pretty much X and Z plane, so it's moving. This is our plane right here. It's moving downwards. Now our velocity is moving from our x and y plane to moving this way in a directional velocity. Now, what's important to us is to simply find the magnitude of the induced EMF. Now, we know that the electromotive force can also be equal to the cross of velocity times the vectors of velocity times the vectors of the magnetic field. So we're just going to do the cross product of that. So velocity cross B, then B, or I, or J, or K. So what we have here, so we have 1.5 meters per second and 2 meters per second. Now we have no K value, so that's 0. And then we're going to have negative 0.12, which is I, 0, since we have no J value for that, and then 0.15 Teslas. So, very simple, solving for I is then going to be 2 times 0.5 here. 2 times 0.15, which is then going to be 0.31 or 0.3 multiplied, and then find the cross of these, which should just be 0, so minus 0, which should be 0.3 I. Plus, and then find for our J is then going to be these two cross multiplied by 0, which is 1.5 times 0.5, which will just be 1.5 times 0.5, right? 0.15. 1.5 times 0.15, there we go. This would be 0.225. And this one, 0.5 is negative because that minus J, how the cross product is. I'm just doing this very simple and fast. Okay, is these two. Which means 1.5 times 0, 0, and then K, which is going to be negative. But this is negative times negative, so 0.2 times 2, 0.12 times 2, 0.24. Technically supposed to be negative on the side, so subtracting turns into a positive, so it's just plus 0.24 K. So pretty much the cross is then going to give us B cross B is then equal to 0.3 I plus 0.225 J plus 0.24 K. Here. And then we're then going to find the electromotive force, because we still have to find what's the induced, which is then going to be E multiplied by Y cross B, so then B equals 0.3 I volts per meter multiplied by what we have. And 0.08 meters, because we're given centimeters, which is then equal to 0.024 volts. So that should be our answer, 0.024. So then on to part G. So which one is higher? What is the higher potential? So the higher potential is moving in a positive direction, pretty much from A to B. That means our higher potential will be B, because the X component is pretty much moving from our A here to our B side. So our higher potential will be B. Then on to the next question. This one, there we go. That was close. Now for part H, now we're still going to be the same figure which we had in the previous one. A rectangle with a rod with a field all around it. Now this time just moving in one direction. Or pretty much, it's saying that the magnetic force on a moving rod and slideway generator has a magnitude of 0.06 newtons. At an instant, the resistance in the current is 0.75 ohms. The rod is 0.19 meters long. The magnetic field was perpendicular to the plane of the generator. It's a magnitude of 0.550 Teslas. Find the speed of the rod. So you have to find the velocity. Now this time we're given both newtons and ohms. So to be able to figure this out, we know that force is equal to R. Field times the current times the length. So if we're given newtons, we know what force is, we know what Tesla is, and we know what R length is. Now at the same time, our current is equal to electromotive force divided by resistance. And electromotive force is equal to our velocity times our field times our length. So current is equal to velocity times field times length divided by our resistance. So we're just going to be inputting this current back into this formula. So where force is then equal to our field times length multiplied by current, which is now velocity times field times length. And then, well, this would be, let me go back real quick. Multiplied by then resistance. So this would then just turn into force is then equal to velocity times e square of field times e square of length, all divided by resistance. So obviously we then gotta figure this out. Multiply resistance on both sides, and then just divide by our field and length, which would then turn into velocity is then equal to force times resistance divided by our field, magnetic field squared, multiplied by our length squared. So then we'll just input the values given to us. Our velocity is then equal to force 0.06 newtons multiplied by resistance of 0.75 ohms divided by e squared over our magnitude, which is 0.55 Teslas squared, multiplied by as well 0.19 meters squared. That's going to give us our velocity. So we're just going to throw this all into one big equation, 0.06. Let me separate these. Times 0.75 divided by our 0.55 squared times 0.19 squared. And that's going to give us a velocity of 4.12 meters per second. And that will be the velocity given to us. All right, that is all the parts here. And that will be everything today. Thank you.